Today's presentation on the formulation of alternative cement matrix for solidification, stabilization of nuclear waste will be presented. To do the introduction is Dr. Patricia Pavier. Dr. Pavier is the Technical Group Manager of the Radiological Materials Group in the Nuclear Sciences Division at Pacific Northwest National Laboratory. She's also the chair of the Gen 4 International Forum Education and Training Task Force. Patricia.
Thank you so much, Bertha. Good morning or good afternoon, everybody. It's a pleasure to be here and to have Mr. Mathieu Decampos with us. So he's one of the 3 students who won the elevator pitch challenge contest at the last GIF symposium meeting in October 2018 in Paris. And as a result, we decided that the prize will be for him to give this presentation. So thank you, Mathieu, for allowing us to have you as a presenter today. So he's a second-year PhD student at the University of Lille, more specifically within the solid chemistry axis of the catalysis and solid chemistry unit. He's a member of the research team Cement. It's the chemistry, materials, and processes for sustainable nuclear activities. This research team is involved in a joint laboratory between the University of Lille and the industry, Orano, for a joint research laboratory on fuel and uranium chemistry. This laboratory is also focused on generating added value to the fuel cycle byproducts and optimizing nuclear processes. The aim is to increase the technology readiness levels for future industrial application. His PhD research goals at adding value to radioactive metallic materials by considering them as reagents for the synthesis of cementitious matrix. His research activities, funded by Orano, are based on a multidisciplinary approach combining civil engineering and solid-state chemistry. In 2017, he graduated from the University of Artois in France with a master's degree in materials chemistry for energy and the environment. So again, thank you, Mathieu, for volunteering to give this presentation, and I give you the floor. Thank you, Mathieu.
Thank you, Patricia. So, hello everyone. This presentation will be composed of 3 main parts. A third part introducing what nuclear waste is. It will discuss of the nuclear waste management system in France while mentioning the French nuclear system and addressing the problems of dismantling nuclear installation. The second part will discuss of phosphate cement matrix and Portland cement for the stabilization and solidification of nuclear waste. The first and last part will talk about my thesis work. For a reason of confidentiality, only the key point will be treated. Let's start with the question, what is nuclear waste? It is any material without any use, which contain radionuclide in higher concentration than the value considered admissible for such materials. We can then ask ourselves many questions about nuclear waste. First of all, can we magically make it disappear? What should we do with nuclear waste? Do they have an impact on the environment? This being said, nuclear waste raises many questions. I will try to answer them during this presentation. First, let's start with the question what to do with nuclear waste. Due to their different physico-chemical nature, it is necessary to be able to classify them according to the level of radioactivity. Then it's necessary to manage them according to the half-life time of the radioelement present. Depending on the nature of the radioelement present, the radioactivity is different. For example, the management of radioactive waste by natural decay, which consists in waiting for the waste to be no longer radioactive. Another way is surface storage for low and intermediate level waste, and finally, deep disposal for high level waste. We can then ask ourselves the question, how are they stored in a way that is safe? How to classify them? That's what we will see in the next slide. The half-life time allowed to classify them. This half-life time can be decomposed into three main classes: very short-lived waste, short-lived waste, and long-lived waste. Now it's meant to categorize them according to the level of radioactivity. There are four categories of radioactivity in the French system: very low-level waste, intermediate waste, and high-level waste. This classification allows to have 6 categories in total. Depending on the categories, there will be a different storage and management. For example, very low-level radioactive waste with a very short lifetime is managed by decay. Deep storage of short-lived and long-lived intermediate and high-level radioactive waste is being studied. Now, let's talk about the volume of radioactive waste and its level of radioactivity. In this slide, I'm talking mainly about the French nuclear waste. According to the graphs on the left, it can immediately be seen that high-level waste represent 85% of the radioactive, but only 0.2% of the total volume of radioactive waste. This graph also shows that most of the radioactivity is concentrated in only 10% of the volume of nuclear waste. What about the other 90%? It is simply low and intermediate short-lived radioactive waste represent 70% of the total volume of nuclear waste, and very low-level radioactive waste represent 31.3% of the total volume of waste. This volume comes mainly from maintenance and dismantling operations in the nuclear industries. Waste management requires development of specific solutions adapted to the hazardousness. In France, more than 60% of the nuclear waste come from the nuclear power industry. We will now focus more specifically on the French nuclear system and waste generation. Where does the waste from the French nuclear cycle come from? The French nuclear cycle begins with the extraction of uranium ore and then its concentration in uranium-235. This enriched uranium is then sent to the fuel fabrication unit. It is then used in the reactor before being reprocessed when used. The French nuclear power park is composed of pressurized water reactors. The many stages of the French nuclear cycle produce nuclear waste. Most of the nuclear waste produced come from manufacturing plants, nuclear power plants, and reprocessing plants. The waste produced come from dismantling of old generation and maintenance operation. It can also be noted that the generation of short-lived and intermediate-level radioactive waste, FMAVC in French, come largely from the nuclear power plants and the reprocessing plants. High radioactive waste is produced in the reprocessing plants. In summary, the French nuclear cycle is a closed cycle where 96% of the fuel is recycled. The remaining 4% corresponding to fission end products, where these different wastes will be sent after they have been generated. Let's look at the three main ways of conditioning nuclear waste. We have vitrification of fission elements in glass matrices, stabilization and solidification of waste in cement matrices, and finally packaging. The common point of these different packaging routes is storage. What are the different storage routes? The French Radioactive Waste Management Plan describes the management method for the different categories of radioactive waste. This plan provides 4 radioactive waste management solutions, 2 in use and 2 in progress. The operational management solutions are a storage center for very low-level radioactive waste and a storage center for low and medium-level radioactive elements. The 2 other solutions under study are near-surface storage, and the second solution under study is a deep storage facility for high-level and intermediate radioactive waste. The dismantling of the French nuclear industry leads the generation of many waste, as a generation of very low radioactive waste. This waste is stored in suitable surface facilities. These facilities consist of storing them in a cell dug into the clay. Why clay? Clay is composed of minerals, solid substance characterized by a particular combination of chemical elements. Those of clay belong to the family of silicates, made up of silicon and oxygen atoms, but also aluminium, iron, calcium, and potassium. Within the clay, they are organized in sheets stacked one on the top of the other, like a millefeuille. The clay has the power to fix the majority of chemical elements. The facilities also have a system for collecting infiltration water. Waste protection is ensured by 3 barriers: a synthetic membrane around the waste, a clay layer under and on the side of the cell, and finally an upper layer of clay to avoid external aggression. The management of low and intermediate level waste is slightly different from the previous storage method. This time, the waste is stored in a reinforced concrete cell. This cell can accommodate many types of waste package, such as drum and concrete package. Once the cells are filled, a blocking material like gravel is inserted to prevent any waste falling out. Then a concrete cover is placed as well as a polyurethane layer to prevent water infiltration. These structures have been designed to be resistant to seismic risk. As with the storage of low-level radioactive waste, these structures are built on a clay layer. Deep storage is an ongoing project called CGO. The theoretical commissioning date is planned for 2030. The purpose of the storage is to protect the population and the environment from the danger of radioactive waste. The waste stored in the center will be long-lived intermediate and high radioactive waste. The storage area is located 500 meters under the surface, more particularly in a clay layer. This area was chosen for its geological properties that slow down radionuclide in case of an accident. This project is also based on the principle of reversibility. The waste should be able to be removed when a specific solution has been found. Waste storage is split according to their categories. Waste handling will be remotely operated from the descent of the waste to its storage location. In conclusion, radioactive waste management is complex because it involves many types of storage, and this system must meet 2 main priorities: the protection of people and the environment. To talk about this challenge of dismantling nuclear power plants, there is nothing better than an example. The first French reactors were uranium graphite gas reactors. Their dismantling was carried out in several stages. For example, fuel was encapsulated into aluminium cases. The reprocessing of this fuel is divided into several stages of dissolution of chemical elements present like magnesium and uranium. Then all the waste is cemented for storage. It is necessary to control the reactivity of this element in order to avoid the generation of dihydrogen. in the cementitious matrices. This generation can present a risk for nuclear installation. To reduce the risk, it is necessary to use specific cementitious matrices. This is the case of the metallic aluminium. The reactivity of aluminium metal depends on the pH of the porous solution of the cementitious matrices. Aluminium is reactive for pH value below 4 and above 9. In both cases, there is the production of dihydrogen. Between 4 and 9, we are in the passivation zone. This corresponds to the creation of a protective layer around the metallic aluminium. It is alumina. This layer protects the metallic aluminium from chemical aggression. It's like a barrier. The cement compatible with this pH zone is the phosphate cement. The literature reports a lot of work on the solidification and stabilization of waste and hazardous materials. This is the case of Wong's studies, which is studying the stabilization solidification of lead-containing waste. In this study, he compared different formulations and type of cement, Portland cement, which is the most widely used cement in the world, and the phosphate cement. This results in the figure on the right show a significant decrease in the amount of liquid lead and when using the phosphate matrix. Compressive strength results show a decrease in performance compared to the reference. From these two figures, it can be noted that in the case of Portland matrices, there is a physical integration of lead, whereas in the phosphate cement, we have a chemical integration of lead. Thus, for lead stabilization solidification, the use of phosphate matrix is preferable. Why do we have this difference between these two cementitious materials? We can wonder what is the major difference between Portland cement and phosphate cement. The answer is very simply, it is the reaction mechanism of setting. In the case of Portland cement, it is an hydration reaction, whereas in the phosphate cement matrix, it is an acid-base reaction. Another difference between these two materials, it is the environmental impact. As the phosphate matrix requires less energy than the Portland matrix, this difference impacts in the amount of carbon dioxide. The quantity is 3 times less in the case of phosphate cement. This difference makes the phosphate matrix an eco-responsible materials. The phosphate matrix waste was first used as shotcrete, then as a repair material. It was in the 70s that the first premix were created. Now, research on this matrix increased. Another notable difference in it is the difference in pH of the porous solution. For Portland cement, the solution has a pH greater than 13, while for the phosphate matrix, the pH is between 6 and 8. This clearly shows an incompatibility of the Portland cement matrix with metallic aluminium. The work of Codicu et al. Show that many cementitious matrices are not compatible with the incorporation of metallic aluminium, since the quantity of dihydrogen produced is in the order of several liters per square meters of aluminium. Only the phosphate cement show very good results. They are even improved by the incorporation of a corrosion inhibitor. How to formulate the phosphate cement? The chemical reaction for the formation of the phosphate matrix is as follows. The acid, which is potassium dihydrogen phosphate, reacts in the presence of water with magnesium oxide to form castrovite. This reaction is characterized by a molar ratio of magnesium to phosphate equal to 1, but the literature says that using a higher ratio, about 6, allows high mechanical performance. One of the disadvantages of using a ratio greater than 1 is the possible hydration of the excess of magnesium oxide. The figure on the right shows the different formulation used in the literature. We can notice that the over-stoichiometric formulation is much more present. But why? The answer is very simple. The stoichiometric matrix with a molar ratio of magnesium to phosphate equal to 1 is characterized by swelling, which is not the case of another stoichiometric matrix. What is the effect of this excess of magnesium oxide? It is a chemical effect, a physical effect, or a physico-chemical effect. It is one of the studies I have carried out. For this, I have used two types of mineral additive to substitute the magnesium oxide. It is fly ash and silicathium. First, I observe the effect of the amount of mineral additive on this stoichiometric matrix. I quantified the volume variation of the sample as a function of the mass ratio found to cement introduced. The photography on the right, on the left at 28 days samples show that the swelling decreases and disappears with the increase of fine division. This is more visible on the graph. The area in red corresponds to formulation with swelling and in green without swelling. Between the two zones, the sample show cracks. These results are identical whatever the final use. The formulation with a mass ratio fine to cement equal to 1 has been chosen for my work. But what is the cause of this swelling? Additional studies were conducted on this stoichiometric matrix. The image on the left shows a three-phase segregation. These phases have been analyzed. It appears that the lower phase contains a large quantity of acids. This quantity decreases on the other phases. X-ray diffraction analysis also shows a difference in composition. Thus, the addition of mineral additive avoids the phase segregation and homogenizes the components. It is the amount of casterite present the same. To verify the role of the other stoichiometric magnesium oxide, we have the idea to compare three identical formulations. The only difference is the final use. We have a mass ratio fine to cement equal to 1, and we use the previously used fine and magnesium oxide as a reference. I recalculated the molar ratio to magnesium to phosphate for the matrix with magnesium oxide. It is another stoichiometric matrix with a molar ratio magnesium to phosphate equal to 5.38. The decomposition of casterite occurs at 100 Celsius degrees, which allows of 6 molecules of water. The yield of casterite is then calculated. The result at 7 days give a yield of 33.4% for silicathium, 40.7% for fly ash, and 46.4% for magnesium oxide. This confirms the physical role of other stoichiometric magnesium oxide on other stoichiometric matrices. This difference is due to the approximation. And in the case of magnesium oxide matrix, the difference comes from the fact that more magnesium oxide is available to react. The difference in mechanical performance would then come from the quantity of casterite. In conclusion, depending on the mechanical performance, the field of application will be different. For structural materials, a strength greater than 60 MPa is expected. Formulation with lower resistance may be used in the field of stabilization and solidification. It is possible to work on the stoichiometric matrix by substituting other stoichiometric magnesium oxide with powdered waste to create a cheaper matrix. However, the addition of fine reduces mechanical performance. The formulation is therefore a complex field with many parameters influencing the physical-chemical properties of cementitious materials. Now, one of my current work is the study of dimensional stability. We have seen the impact of fine on the phosphate matrix. Now we will see the effect of mineral addition in the Portland cement matrix. Portland cement is an hydraulic binder produced by calcinating a mixture of limestone and clay at a temperature above 1,400 Celsius degrees. After grinding, the clinker is obtained. Here represents the main hydration reaction that takes place in Portland cement. In the case of the phosphonation matrix, we have substituted the other stoichiometric magnesium oxide, but how to integrate a mineral additive into the Portland cement? The integration of mineral additive into a Portland cement mortar can be done in different ways. I will present the simple addition case to you. It consists of simply adding the mineral additive to a given formulation. This integration highlights a maximum percentage with high mechanical performance in compression. In this case, from 60 MPa at 14 days with 10% of fly ash addition. But why does this performance decrease over 10% of fly ash? The compressive strength depends essentially on the granular skeleton. The addition of fine will fill the void in the cementitious matrix and increase mechanical performance. There is three different cases. The first case where the quantity of fine is not sufficient. The second case with filling of void. And the third case with destabilization of the granular skeleton. Thus, only the second case can increase mechanical performance. This allows to increase the compactness. The work of Benachur et al. Shows the same result. The work shows that the maximum compressive strength is reached with 15% incorporation of filler addition. The addition of mineral additive also decreases with permeability. That is to say, the material is less permeable, which is a benefit in the case of maintaining dangerous elements such as radionuclide. In the context of my thesis, I must respond to the integration of nuclear waste for stabilization, solidification of nuclear waste. The formulation must meet some specification, mechanical strength, sufficient workability, thermal resistance, and optimized incorporation. This can be summarized by the diagram on the right. My work makes it possible to demonstrate the feasibility or not of the different formulation, the objective being to increase the scale and unlock the technological loss. I'm going to tell you about a specific work I had to do in the laboratory to allow me to work on small scale, which save raw material during the formulation phase. Civil engineering tests are carried out on large sample quantities and volume. However, for reason of raw material saving, the miniaturization of the test was one of the key points of my thesis. In the fresh test stage, this has gone through the miniaturization of a mini Abrams cone by a factor of 4. This allows me to quickly evaluate the rheology of my small-scale formulation. It consists of filling a cone with the cement paste and then lifting it. Once the cement paste has been sprayed, the spreading diameter is measured in two orthogonal diameters. The relative spread is defined as the ratio of the spreading diameters to the largest diameter of the cone. For future use, it has been defined that the relative spread should be greater than 2.5. My results show that the significant impact is due to the physico-chemical properties of the powder added, like the specific surface. This specific surface plays a key role on the water demand and on the rheology of the cement paste. Afterwards, they are mechanically tested. The characterization of the mechanical performance required the implementation of a small-scale setup. The tests carried out in the civil engineering laboratory are done on prismatic samples of 16 centimeters by 4 by 4 centimeters. After flexural tests, give 2 cubic samples in compression. Laboratory tests are performed on samples which are volume 29 times smaller, which allow me to have 4 cylindrical sample of 7.5 millimeters in diameter by 13 millimeters of height. This setup consists of a microcontroller connected to an amplifier that amplifies the signal from a force sensor. It's also connected to a position sensor to acquire the displacement of the axis during the compression test. The entire assembly is adapted to an uniaxial press using parts printed by a 3D printer. The first test showed a significant difference for the same formulation at the same time in compressive strength, with a small scale test having a lower strength. I implemented a thermal protocol to solve it, but why? Work by Lee et al. Has shown that the heat of hydration which depends on the volume of the sample. They have also shown an impact of compressive strength. Based on the Arrhenius law, it describes the constant speed of the reaction as a function of the activation energy and the temperature. An increase in temperature increases this constant and thus the reaction kinetics. Thus, the reaction kinetics depend on the temperature. By increasing the temperature of the sample, the reaction kinetics should be increased, and therefore the amount of binder phase present also, and the mechanical performance also. The development of mechanical performance is linked to the amount of binder phases present. To verify this, I set up a thermal curve at 40 Celsius degrees with different time between 2 and 24 hours of cure. All the samples are tested on the same day. Here, the results are obtained to one day. We can see an exponential increase on the compressive strength as a function of the cure time at 40 Celsius degrees. These results allow me to say that a thermal cure of 8 hours at 40 Celsius degrees allow me to have similar results compared to the large scale at 1 day. The dismantling reactor generates many wastes of different physico-chemical nature. This is why the development of new adapted cementitious matrices is important to ensure safety, protect people, and the environment for their toxicities. Cement formulation requires the implementation of specific according to the intended use, while respecting the reactivity of the waste. The many parameters influencing the properties of these cementitious materials make it a very complex system. In addition, the implementation of new formulation involves many steps, as physical and chemical characterization. These analyses make it possible to improve the understanding of these materials and the phenomena involved in the case of the stabilization and solidification of nuclear waste. The use of these new materials will make it possible to respond to various challenges, whether they are safety, technological, environmental, or financial. This work is carried out in the UCCS unit, more particularly in the LR4CU, which is a joint research laboratory with OANO and at Central Lille Civil Engineering Lab. I thank OANO and Lille University for funding my thesis. I also thank my supervisor, the technical staff of the lab, and finally my colleagues. Thank you for your attention.
Thank you, Matthew. Oops. If you have questions on today's presentation, please do take the time to type those into the Q&A chat pod. While questions are coming in, we'll take a quick look at the upcoming webinar presentations. In June, a presentation on the interactions between sodium and fission products in case of a severe accident in a sodium-cooled fast reactor. And in July, a presentation on security study of sodium gas heat exchangers in the framework of a sodium-cooled fast reactor. And in August, a presentation on lead-containing mainly isotope lead-208, new coolant, moderator, and neutron reflector for innovative fast nuclear reactors. So there is a question, Matthew, I don't know if you can see the question pod. It reads, yes. Probably I missed what the form of the waste you are destabilizing, liquid or solid. Would you clarify that?
I don't see the question.
Regarding the form of the waste in which we're stabilizing, whether the waste is a liquid or solid.
Yes. Depending on the physical state of the waste, there are different formulation type. I know that some people are working on the stabilization of oil from nuclear waste. I'm working on the stabilization of solid waste in my case, but I know that some people are working on liquid waste.
Are there any other questions for today's presenter? So there is a question, does the solid waste act as aggregate in typical concrete?
In my case, yes, I work on different type of integration, and now I'm working on the addition of this waste as an aggregate.
Have you performed any durability tests?
No, this is future work. I'm working on the optimization of the formulation to have the good performance, and when we will have the good formulation, we will do some durability test and lynching test.
Talk of, I'm not sure what this word is.
It is a leaching test.
What is the performance indicator?
Yes, I don't have a performance indicator because my work, I work on some ways that is, and my work are confidential. That I can't respond to that, but I don't have any performance indicator in that case.
What is the most difficulty you think when mix cementitious materials in a waste stream?
The most difficulty, I think, it is in the demand, the water demand, because if you want some workability for your formulation, if the waste is so little, you will have some troubles for workability. So to summarize, I think in the fresh state, to create the fresh state is the most difficult part of that.
What are the typical particle sizes that you have used in your aggregate?
In my case, I'm working on fine addition, and it's like 5 micron. And I'm also working on this the substitution of some parts of the sand to increase the percentage of waste integration.
Are you going to try phosphate cement with liquid waste streams?
In my thesis work, no, but it's a good idea because you can I know that on the literature that some phosphate cement are created from mixing magnesium oxide and phosphorus liquid. So if you create a liquid with phosphorus and waste, I think you can create a phosphate cement.
Why? Oh goodness, they're really coming in. Why do you think MKP or other cementitious materials would be better than OPC for waste immobilization?
I know that in the case of MKP, in the case of the leads that I speak, there are the formation of phosphate phase, and the solubility of this phosphate phase are not we know that phosphate phase are not soluble. Yes, are not soluble. So in the phosphate cement we can have physico-chemical integration, but in Portland cement it depends on the chemical of the waste.
Of MKP cement, so in your knowledge, is this the only solution for aluminum waste? Also, you say the other people are working on liquid waste, so it appears it can handle both solid and liquid waste. But is there a situation MKP is not useful?
I know that some other cements are compatible with aluminium, but I don't know now. But let me come back to you if you want, and I will send you an email if you want to discuss about that.
Very good. How is the heat of hydration compared to OPC?
In my case, I don't measure the heat of hydration, but the heat of hydration of MKP of phosphate cement depend on the ratio of this mass ratio of water to cement.
Have you also considered using geopolymers?
In my thesis work, we don't work with geopolymers, but some of my advisors are working with geopolymers.
Are the hydrated phases well characterized? I mean, are the stoichiometry of the hydrated phases well quantified so that one could use this in hydration models?
I characterize the hydrated phases by X-ray diffraction and TGA, TDA, and I just quantified and identified the phases, but I don't know in that case if the stoichiometry of the hydrated phase has been well quantified.
What about amorphous phases?
In the case of magnesium phosphate matrix, in the stoichiometric matrix, we have an amorphous phases. This is well known in the literature. I think in the last month, a publication has been sorted on the characterization of the amorphous phases. But in my case, I don't do some Rietveld calculation of my phases. So far, I don't calculate the percentage of amorphous phases. But for me, the apparition of the amorphous phases come from the fact that we have when we work with a stoichiometric matrix, we don't have a good homogenized cement matrix. So the addition of powder can homogenize the component and the phosphate phases in the cement. So it can decrease the formation of these phases because we don't have any swelling in that case with fine addition.
What would some typical sources of radioactive waste that could be stabilized in this method? For instance, rods from nuclear power plant would not be possible for several reasons, so highly radioactive that it would degrade the concrete within years. Also, rods would have to be pulverized somehow. This would cause the pulverizing equipment to become radioactive waste. So what would the sources of waste that could be applicable? I'm not sure. Patricia may want to even chime in on this.
this is a good question. I can't answer to confidentiality, but I will try to answer.
Yeah, let me talk, Matthew.
Okay.
When I see the questions about the rods from nuclear power plant, they will not be going into a cemented waste form. You are working on low activity waste. Am I right?
Yes, I'm working on low radioactive waste, and but I can say that phosphate cement are not durable in high temperature. So using high level radioactive waste can't. So we can't use that cement matrix for high level waste.
What is the main purpose for using supplementary cementitious materials in your mix?
I can't answer due to confidentiality, but I can say that using the addition of supplementary cementitious materials can decrease the price of this cement matrix, because the phosphate cement is more expensive comparatively than Portland cement.
Why do you need the compressive strength to be 60 megapascals?
I need to have a 16 megapascal to respect the specification of my industrial partners. So it's just a number, but I have some formulation under 60 MPa.
Thank you, everyone, for all of your excellent questions. I do want to remind you that Matthew is a second-year PhD student. He won a competition in an elevator challenge, discussion challenge, and was awarded the opportunity to give his presentation today. And you can see we will have very more great things to look forward from Matthew in the future. Thank you very much for your participation, Matthew. It's just been an absolutely engaging presentation.
Thank you.
Thank you, Matthew. I will do good when you're going to defend your PhD. That was outstanding.
Thanks.
I don't see more questions, so I think that concludes our Q&A portion of today's presentation. Thank you again, everyone, for joining, and we'll look forward to seeing you in June.
Thank you, Matthew. Thank you, Bertrand.
Thank you.
Goodbye.
Thank you. Goodbye.